Good morning, everyone. Welcome to Math Monday. I'm Miss Barnes, and the segment that follows is for kindergartners through second graders. Friends, today we're going to be working on a specific strategy called near doubles. In just a second, we'll go through the objective, but you definitely need to make sure that you have a writing utensil and paper ready for our lesson today, as we are going to create another part whole map, and then we will go through our strategies. So our objective is I can use the strategy of near doubles to solve addition problems. Today's tools, we will be using a part whole map. We'll also be using red and yellow counters, and you will need a writing utensil and paper. Remember, a couple weeks ago, we talked about how to create a part whole map if you don't have one. And all you need is a piece of paper, and I'll just rip one out of my notebook here. All you need is a piece of paper, and then remember to create the map, you'll fold it in half. This time we're going to create it just a little differently. And we're going to draw a black line about a quarter down the way. So you'll just draw one black line. And then I'm going to draw a black line horizontally across the page, just like this. And then I'm going to add a box at the top. And this is our completed part whole map for today. So take a second and let's get ready to learn. All right, getting started. Make sure you have your part whole map close to you, and make sure you can either color on it with your colored pencils or crayons or markers, or make sure you can draw in it and erase with a regular pencil. We are going to do 3 problems today if there's time. Let's go ahead and take a look at the first one. Remember, as we're solving word problems, we need to make sure that we're reading the whole question first so that we understand how to give the answer. So our first step here is going to be reading the whole question first. Read with me. Alex has 4 apples and I have 5 apples. How many apples do we have? Write an equation and justify your thinking. Now, as we're getting started today, we're going to talk about a couple of the words that are in this word problem. And the first one we are going to talk about is the word equation. So I'm going to take my drawing tool here, and I'm going to highlight in yellow the word equation. Equation is an important math word, and an equation is this down here at the bottom of your screen. An equation always has an equal sign. If it doesn't have an equal sign, it can't be an equation. So that's the first really important word. The second really important word is justify. And justify means to prove what you're thinking and how you got your answer. So as we're working today, we're going to use our model on the part whole map to justify the way that we're thinking. We're also going to write some stuff on the right side of your screen that will help us justify our answer at the very end. So let's get started. We're going to go back and reread the question again, and then we'll get started with our model. Alex has 4 apples and I have 5 apples. Let's stop there. We're just going to draw a line. Alex has 4 apples. How do you model that in our part whole map? So one thing I'm going to do is I'm going to take one of these counters and I'm just going to move it. Maybe, if it lets me. There. Now I can do it. I'm just going to move the counter over into, so I'm going to move a red counter up above the word apples because I want to use the red counters to show how many apples Alex has. Then what I'll do is I'll take the red counters and I'll move them into the part whole map. And I need 4 of them because Alex has 4 apples. So there's 1, 2, 3, and 4. Okay. Now the second part of that sentence says, I have 5 apples. So I'm going to model with the yellow counters how many apples I have. And then we'll count them. 1, 2, 3, 4, and 5. Now I need to write an equation that goes with my model. If I'm going to do, as I'm doing that, I'm going to change my marker color. And I'm going to write down below my equation. So the first number in the equation, the first addend, is going to be 4 because that's how many apples Alex has. The second number in the equation, the one that follows the plus sign, is going to be 5 because that's how many apples I have. Now, when we talk about the strategy of near doubles, it's really important to remember your doubles. So can you find a double fact that is close to 4 plus 5? Remember, doubles are facts that have the same number in both addend positions. So the double fact that I remember easiest associated with this is 4 plus 4. I know that 4 plus 4 equals 8. I also know that 4 plus 5 is the same as 4 plus 4 plus 1. This is how I use that doubles fact when I'm trying to solve for a problem that's really close to a doubles fact. So I know that 5 and 4 plus 1 are equal. So I've done what's called substitute 4 plus 1 into that spot to make it just a little bit easier. So now we can say on the right side of this equation, we can say that we know that 4 plus 5 equals, and then do you remember what we said about 4 plus 4? What does that equal? That equals 8. So we've taken this part out, but we still have the plus 1 at the end. So now I know that 4 plus 5 is the same as 8 plus 1. Then I know that 4 plus 5 is the same as, what's 8 plus 1? Can you tell me? That's right, 8 plus 1 is 9. So now I know that 4 plus 5 equals 9. And I used the near doubles facts to get to my answer. Let's go back to our equation underneath our model. The equation here says 4 plus 5 equals 9. And we can justify our thinking both with our model, we could count the total of counters there, or with our comparison on the right side. That was a lot of steps, and I'm sure you're ready for a break. So take a quick moment here, and we're going to get ready for problem number 2. All right, are you ready for the second question? Here we go. Sam eats 4 tacos for dinner. His sister Roxy eats 3 tacos for dinner. How many tacos did the kids eat in all? Now you'll notice the first thing that I've done is I've placed a red counter above Sam's tacos and a yellow counter above Roxy's tacos. I did that so that I could keep track of who has which color counter. Now we need to go back and reread one sentence at a time, and we need to build our model in the part whole map. The first sentence says, Sam eats 4 tacos for dinner. And then we'll stop there. How do you model that in your part whole map? Can you place 4 red counters in your part whole map? 1, 2, 3, and 4. Great job. Next, the next sentence says, his sister Roxy eats 3 tacos for dinner. Stop there. How do you model that? Pick up your yellow counters and let's count 3. 1, 2, 3. Remember, if you don't have counters, you could just be drawing circles and filling them in on your page. So here's our model. Sam eats 4 tacos for dinner. His sister eats 3 tacos for dinner. Now our question is, how many tacos did the kids eat in all? So now we need to write a statement to answer that question. And the statement I'm going to write says the kids ate blank tacos. And remember, we put that blank here so that we know that they ate some tacos and we have to figure out how many. Let's do that part now. So next we're going to work on our equation. So down at the bottom here, we're going to write our equation, and then we will solve using the blank space on the right of your screen. When we're writing our equation here, we need to start with 4 because there are 4 counters on the left side. Then we're going to add 3 to that number sentence. Now we have to think about solving, and in order to do that, I want you to think of a doubles fact that is almost 4 plus 3. Can you think of one? The one that I would use is 3 plus 3. Do you know what 3 plus 3 is? I knew you did. It's 6. Great job. So I know that 3 plus 3 is almost 4 plus 3. How many more do we have to add to get from 3 plus 3 to 4 plus 3? Well, I know that 3 plus 1 equals 4. And then I have to add the other 3. So I know that 3 plus 3 equals 6. And then I have to add 1 to it, and you know what 6 plus 1 is. 6 plus 1 is 7. So I also know that 4 plus 3 equals 7. So how many tacos did the kids eat? Well, the kids ate 7 tacos. That's all we have time for today, friends. There is one more problem that I'm going to put up for you. And as we are closing out here, if you'd like to copy it down and work on it, you can do so. So here's the last problem that I have for you today. Remember, if you'd like to share any of your work with me, you can find me on Twitter. Your parents can find me on Twitter at MissB_KCPS. It was great having you in class this week. I'm looking forward to seeing all of the work that you're doing. And remember to take care of yourselves. See you next week.
Good morning. Thanks for joining us for Math Monday. I'm Erin Dorsey, and I'm one of the elementary math coordinators for Kansas City Public Schools. The last few segments, we've been working hard solving word problems in math and using the 8 mathematical practices to help us. Today, we're going to continue those lessons using a tape diagram to solve our problems. A tape diagram is a strategy that can be used to solve any word problem. If it sounds new, It's really not. It's very similar to number bonds. And you use number bonds all the way in kindergarten, first and second grade to help you solve problems. A tape diagram is just taking that number bond a little bit further. So let's get into our problem.
Let's take a look at our problem. A Kansas City store has 458 Chief shirts, 212 Royal shirts, and 277 KC hats in their inventory. How many more shirts does the store have than hats? The first thing I want to do is identify the most important information that will help me solve my problem. Do you see any information that we could use? If you're thinking this information here, you would be correct. 458 Chief shirts, 212 Royal shirts, and 277 KC hats. That information is going to help me solve my missing pieces. It's going to help me solve for my missing pieces. Another piece of information that's extremely important is the question, because that tells me what I'm trying to find out. So as I said before, today's strategy is going to be using a tape diagram. Now, you may have heard of this same strategy referred to as a bar diagram. Those are the exact same thing, it just has two different names. So if you hear your teacher or someone else say bar diagram or tape diagram, we're talking about the same strategy. With this strategy, we need to figure out what we're comparing. And we can find that in our question to this problem. How many more shirts does the store have than hats? So what are we comparing? If you said shirts and hats, you would be correct. So I'm going to list those two things off to the side. I have shirts and I have hats. S for shirts, H for hats. For the shirts, I'm going to draw a bar. This is my total amount of shirts. And I know that this total is made up of two parts, and I get those parts from my problem. I have 458 Chief shirts, which is one part, and I have 212 Royal shirts, which is my second part. Together, they give me my total amount of shirts. Now for the hats, I have a total, and that is 277. But if I'm comparing my hats to shirts, that means that my bar for hats needs to be the same size as my bar for shirts. And it's not, is it? I have all of this space here to make up, and that is my unknown. That's what I'm trying to figure out. So the first thing I need to do is figure out what this total is. How do you think I can do that? By adding, exactly. I have two parts and now I need to find the total, and I can find the total by adding. So I'm going to add 458 plus 212, and that will give me my total amount of shirts. 8 ones plus 2 ones is 10 ones. Put my placeholder down, carry the 10. 5 tens plus 1 10 is 6 tens, plus another 10 is 7 tens. And then 400s plus 200s is 600s. My total amount of shirts is 670 shirts. So remember, if I want to make my hat bar the same size as my shirt bar, that means my hat bar also needs to equal 670. Do I have a piece of that total? Yes, I do. 277 is a piece of the total. So I have 670 and a piece. To figure out the unknown piece, I can subtract, and the answer will be my missing piece. So I'm going to go ahead and do that. 0 ones minus 7 ones. Right now I don't have enough, so I'm going to have to break down a 10. That means this would be 6 tens. And I'm going to put the 10 here. 10 ones minus 7 ones is 3 ones. Now I have 6 tens minus 7 tens. I don't have enough right now, so I need to break down this 100. If I break down this 100, this becomes 5 hundreds. And I put my 100 over here. So I have 160 or 16 tens. 16 tens minus 7 tens is 9 tens. And then 5 hundreds minus 2 hundreds is 3 hundreds. This is my missing piece. So I'm going to put that back up here. So that means 277 plus 393 equals 670. If we did our math right, all of that should equal. Let's check it real quick. 277 plus 393. 7 plus 3 is 10. 7 tens plus 9 tens is 16 tens, plus another 10 is 17 tens. Carry. 200s plus 300s is 500s, plus another 100 is 600s. So 670. Yes, it does equal. We got it correct. So let's make sure we've answered our question. How many more shirts does the store have than hats? Okay, well, if the store has 670 total shirts and it only has 277 hats, this missing piece here is how many more shirts it has than hats, and that is 393. So my answer is 393 more shirts than hats. Let's take a look at another problem. The same store sold 304 Royals jerseys in June. I'm going to highlight that because I know it's important. And 34 fewer in July. That is also going to be important. How many jerseys did the store sell in both months? So I need a total. It's going to be for both months. So when I set up a tape diagram, I know that I'm comparing two things. In this problem, what am I comparing? If you said the months June and July, you would be correct. So I'm going to write those down here. June and July. In June, there were 304 jerseys sold. In July, there were some jerseys sold, but it was 34 jerseys less than 304. So that means this right here is going to tell me how many jerseys were sold in July. What operation do you think I could use to find out how many were sold in July? Subtraction, yes. I have a total of 304 jerseys in June, and I know that I sold 34 less than that in July. So therefore, I can subtract. 304 minus 34. 4 ones minus 4 ones is 0. 0 tens minus 3 tens. I'm going to need to break down 100 to do that. So I'm going to break down 100. That means there's going to be 2 hundreds left here. I'm going to put my 100 down here, which is also equal to 10 tens. 10 tens minus 3 tens is 7 tens. And then 2 hundreds minus no hundreds is 200. So in July, they sold 270 jerseys. Am I done? You're right, I'm not done. Because if I go back to the question, it asks me how many jerseys were sold in both months. How am I going to figure that out? That's right. I am going to add my jerseys in June, which is 304, to my jerseys sold in July, which is 270, and that's going to give my total amount of jerseys sold in both months. So 4 ones plus 0 ones is 4 ones. 0 ones plus 7 ones is 7 ones. Or I'm sorry, I made a mistake. Did you catch it? That's right, I was in the tens column, not the ones column, so let's redo that because mathematicians want to be precise. I have 0 tens plus 7 tens, and that leaves me with 7 tens. 3 hundreds plus 2 hundreds equals 5 hundreds. That gives me a total of 574 jerseys sold in both months.
So what do you think? Bar models, tape diagrams, two different names for the same strategy, but it's a strategy that's going to work for you all the time. And it takes your knowledge of number bonds and helps you figure out how to solve word problems that are maybe more complex than what you're used to. The main thing is that you are using what you know in the problem to solve for what you don't know. And that you're using a strategy that allows you to organize your thinking. Now, I'm sure you noticed in the problem, I made a mistake. What did I do when I made that mistake? That's right. I stopped and I went back and I corrected my mistake. I didn't just keep going because mathematicians are precise. One of the 8 mathematical practices is to attend to precision, and that is very important. We attend to precision by making sure that our thinking is organized, that our work is not sloppy and all over the place so that we can understand what we're writing, and that we keep using the right type of language, and we keep explaining our thinking as we go along. All of that allows us to attend to precision while using our background knowledge to solve for what we don't know. I hope you enjoyed your time today, and I hope that when you're solving problems with your teacher, that you can use this strategy to help you. Have a great day. See you later.
Hello, my name is Mary Jo Fender, and this is Math for Middle School. Today we're going to be going over quotient of powers. What you'll need today is paper and pencil. Okay, take a quick second, let's get ready to learn. Our goal today is to use laws of exponents to divide monomials. Now, if you remember last week, we were talking about product of powers. Product means multiplication. This week we're going to be talking about quotient. Notice product and quotient are opposites, so that might give you a hint on the process we're going to use today. Let's take a look at a couple examples from last week's lesson. You'll notice my first example is x to the m times x to the n. And our laws of exponents say if our bases are the same, and our bases here are the same because they are the base of x, I can add my two exponents together. So I would add m and n, whatever those happen to be, and I would get my product of my power answer. So let's stick some numbers in there and see if we can come up with some product of powers. So 12 to the fourth power times 12 to the third power. Remember, our bases are the same, they're 12. So all we're going to do is add our exponents together, which is 4 plus 3, which gives us a final product of 12 to the fourth power. So remember, product, quotient, they're opposite. Adding, what's the opposite of addition? So let's take a closer look at a quotient of a power. So simplify, remember, just means to write in simplest term. So we have 3 to the 6th divided by 3 to the 2nd. And if we take a look and expand these out, I'm going to say 3 times 3 times 3 times 3 times 3 times 3. I'm going to put my fraction bar. Remember, fraction is our term or our symbol for division. And we're going to expand 3 to the 2nd power, 3 times 3. Now, if you remember your work in fractions, anything over itself, so a over a, or a divided by a, is always equal to 1. Now, you'll notice that we have two groups of 3. 3 is in the numerator and in the denominator position. So we can break those apart from the group and say those particular groups are equal to 1. So I'm going to just draw a big number 1 through them. In algebra, we say that it cancels, and most teachers just slash it out or ignore it and move on. So if you'll notice, I have 4 3's left. You'll also notice that they're on the numerator's position, and that's going to become a factor in later work with exponents. So that's going to be 3 to the 4th power. In our denominator, we have 1 times 1, which is 1. So our answer is 3 to the 4th power over 1, or 3 to the 4th power to the 1st. Now, when we talk about fractions, anything over 1 is a whole number, and it can be rewritten. And so when we rewrite this, it would be 3 to the 4th power. So our question, 3 to the 6th divided by 3 to the 2nd, in its simplest form, is going to be 3 to the 4th. Now, did you notice a trick? When we talked about products, we would add the exponents. Notice here, if we do 3 to the 6th, what's the opposite of addition? Oh, yep, it's subtraction. And we subtract our exponents, 6 and 2. We're going to end up with 4. Keep our base of 3, use our exponent of 4. Our answer is 3 to the 4th. Notice that this is the same as if we did it in expanded form and canceled. That's a quick shortcut, especially when you get good at it. It will save you a lot of time. So let's take a look at another one. Notice we have 2 to the 8th divided by 2 to the 5th. The first thing we have to check is our bases. Do we have the same base? Yes, we do. The base is 2. Because our base is 2, we can, remember what's the opposite of adding? Yep, subtracting. We're going to subtract our 8 and our 5, our exponents. So 8 minus 5 is 3. So 2 to the 8th divided by 2 to the 5th in simplest form is 2 to the 3rd. Okay, so let's try another one. This time, we're not going to have a base that's a number. We're going to use a variable. So we're going to simplify x to the 9th divided by x to the 4th. Remember, the very first thing we have to check is, does the powers have the same base? And this time, our base on both of our powers is x. So yes, it is. And now we can apply our laws of exponents. So remember, anytime we're dividing, we can actually subtract our powers and come up with the same answer as if we wrote it in expanded form. So if we said x to the 4th power, x to the 9th power minus 4. You're going to ask yourself, okay, what's 9 minus 4? That's 5. We're going to keep our base, x. Our exponent now becomes 5 because we have 5 extra variables, which are x, in the numerator's position. We don't need to write the 1 underneath when we do this because it's already in simplified form. So let's try another one. This time we're going to use coefficients with our exponents. And basically when we do this, we have two separate problems. We have to break our coefficients out, and then we have to work with our powers. So our first problem is 15 over 5, or 15/5. You can say 15 divided by 5 if you want. You need to simplify those coefficients. Now sometimes they'll simplify, sometimes they won't, sometimes they'll turn into whole numbers. You need to be expecting anything. But you should be thinking to yourself right now, oh, I know what 15 divided by 5 is. 15 divided by 5 is 3. So our coefficient for this particular problem is going to be 3. Do we have the same bases on our powers? Absolutely, we have the base of y. So we're going to say y to the 7th power minus 3. Remember, we're going to subtract our exponents. That's our shortcut. And what is 7 minus 4? Or I'm sorry, gave you the answer. 7 minus 3, that's 4. So our power is y to the 4th. Now to make our final answer, we're going to take our answer from our coefficients. We're going to take our answer from our power, and we're going to put them together. So our final simplified form of 15y to the 7th divided by 5y to the 3rd is 3y to the 4th. Remember, when you're working with exponents, you have to break them apart. So let's try another one. Notice we have 7x to the 6th divided by 9x to the 2nd. Break your coefficients off. Can you simplify 7/9? I hope you said no, because it is already in simplest form. Now let's break our powers off. So if we have x to the 6th divided by x to the 2nd, do we have the same bases? Yeah. So all we have to do is subtract our exponents. 6 minus 2, yep, that's 4. We're going to put our two sets of answers together. So our simplified form is 7/9 times x to the 4th. Now you may see some teachers, because x to the 4th is actually a whole number, keep it in the numerator's position. So you could actually say 7x to the 4th divided by 9. And it's the same thing, it just looks a little differently. Let's try another one. This time we have 28 n to the 11th divided by 18 n to the 3rd. Break your coefficients out. 28 over 18. What does that simplify to? Okay, you can divide both by 2. 28 divided by 2 is 14, and 18 divided by 2 is 9. Now we can keep this just like this as an improper fraction, or we can actually write it as a whole number. We can say 1 5/9. Now how I got that answer is I know 9 is going to go into 14 one time. That makes a whole. I have 5 left over, so that's my 5/9. Now I'm going to do my powers, so I'm going to say n to the 11th divided by n to the 3rd. Check my bases. Are they the same? Absolutely. So I can use my laws of exponents and say 11 minus 3. 11 minus 3 is 8. So my answer is n to the 8. Put your two forms together. Now this one you can write in a couple of different ways. You can say 14/9 n to the 8th, or you can say 1 5/9 n to the 8th, or remember n to the 8th is really a whole number, and I can write that as n to the 8th over 1. I can actually say 14 n to the 8th divided by 9. It all depends on what you're going to do with this, on how you're going to write this. So let's try one more. I have 36x to the 12th divided by 9x to the 8th. Remember, break your coefficients apart. 36 over 9. What does that simplify to? I hope you notice that 36 can be divided by 9 evenly. That gives us 4. And x to the 12th divided by x to the 8th. Do we have variables that are the same as our bases? Absolutely. So we can say x to the 12th divided by 8. What does that equal? 4. So we can say x to the 4th. Now, all we have to do is put our coefficient and our power together. So our answer is 4x to the 4th. Now it's your turn. I have 3 practice problems for you to do today. That concludes our lesson for today. So let's take a quick review. Remember quotient of powers. We need to subtract the exponents as long as we have the same bases. If you have coefficients, break those out first. Simplify as far as you can. Then work with your powers. Get that in simplest form and then put your two together. Thank you for joining me today. It's been my pleasure having you in class. My name is Mary Jo Fender, and I'll see you next week.
Hello, my name is Marcelina Lirius, and welcome to Math Monday. Our lesson for today is solving systems of linear inequalities. We're going to apply what we have learned in solving systems of linear equations. And before we start, I want you to take your notebook and your pen and be ready to learn. At the end of this lesson, you should be able to solve or find solution to a system of linear inequalities. Then we're also going to interpret the solution. So a system of linear inequalities consists of 2 or more linear inequalities. And to solve the system, we're going to first graph each linear inequality independently. So which means that if you have the line x less than or equal to x plus 4, we're going to graph this first, then graph the second one, and the solution to a linear inequality is a half plane. Which means that the ordered pairs on this half plane would represent the solution, and also any point on this half plane, okay, in this region or this region would satisfy the corresponding inequality. So the solution to the system will now be the intersection of the 2 overlapping solutions. Okay, let's start first with a quick review of the inequality symbols. So if we have a strict inequality greater than or less than, we're going to use dashed line for our boundary line. And for the non-strict inequality, so greater than or equal to, less than or equal to, we're going to use solid line. Okay, so let's try the first one. Y is less than 2x minus 5. Our reference graph here will be the linear equation y equals 2x minus 5, which is of the form y equals mx plus b, and that our m is 2 or 2 over 1, and b is negative 5. or 0, comma, -5 as the y-intercept. So what we're going to do here is plot the y-intercept 0, -5, then interpret the slope again as rise and run. So 2, 1, 2, rise and run, 1, 2, 1. Then, okay, let's look at the boundary line. This is a strict inequality less than, so therefore our boundary line will be a dashed line. Okay, you have less than, so therefore you have a dashed line. So let's use a dashed line for this boundary line. Okay, now which side of the line are we going to shade to represent the solution? Okay, so the first step is to find the test value, and the most convenient point is the origin, or the point 0, 0. So we are going to substitute these values to this inequality. Y is 0 here, less than 2 when x is 0, 2 times 0 minus 5. And when we simplify, we have 0 less than 0 minus 5. 0 is less than, so that will be 0, -5. And this is a false statement. So what do we do? So we were checking that to see if 0, 0 is a solution. So we arrive at a false statement. This means that this point 0, 0 is not part of the solution. So we are going to shade the other side. So this is now the half plane that represents the solution to this y is less than 2x minus 5. Okay, y is less than 2x minus 5. Next, on this second line, y is less than 2x minus 5. Again, it's a strict inequality, and we are going to use dashed line for our boundary line. And since this is our reference line is still our original 2x minus 5, I will just replace this with the green line to represent our new line, 2x minus 5. And it says greater than, okay? Which part of the region, or which side of the line are we going to shade for this second one? Okay, for this second one. Let's use 0, 0 again as our test value. So when our test value is 0, 0, let's substitute this into the inequality 0 greater than 2 times 0 minus 1. So 0 is greater than 0 minus 5. 0 is greater than -5, and this is a true statement. How do we interpret this? So if R 0, 0, okay, we test this value and we arrive at a true statement. So we are going to shade that region where the point is. So we're going to shade this region. The half plane here represents the solution to the inequality y is greater than 2x minus 5. I'll pause. You process the information. Why we shaded the right side for y less than -2x minus 5, then the other side for y greater than 2x minus 5. Okay. Let's have our first example. We're asked to find the solution to the system of linear inequalities. We now have this 2 linear inequality. As I have said earlier, to find the solution to the system, we're going to graph the 2 inequalities independently. So I already have here, I used a graphing calculator, Desmos graphing calculator, to find the solution. So let's just confirm, you now have y is less than x minus 3. That's our first line here. So our slope, okay, if we're referring to the line, okay, our reference line y equals x minus 3, our slope m is 1, and our b is -3 or 0, -3. Okay, so again, this is a strict inequality, less than, so therefore we use dashed line. That's the reason why you have the dashed line here. Notice that in this graph here, you use dashed line. Now let's see if this is really the region that this part here is really the region that shows the solution to y less than x minus 3. Okay, so if you have 0, 0, let's test when x is 0 and y is 0. Substitution, so when you have 0 less than 0 minus 3 is negative 3. And this is a false statement, okay? False, so which means this 0.00 is not a solution. The reason why we shaded this right side of the region, or I mean the right side of the line. Okay, as I've said, we are going to graph each inequality separately. Okay, so the second line is, the second inequality is y is greater than 3x plus 1. Let's see the graph on the next page. You now have y is greater than 3x plus 1. I mean greater than or equal to. If we're looking for that line, y equals 3x plus 1, we know that this is our slope m, which is 3, and the y-intercept b is 1, or the point 0, 1. Okay, so let's see if this is the right graph. Let's go back. Let's first examine the boundary line. Will it be a dashed line or a solid line? So you have greater than, the symbol here is greater than or equal to. So our boundary line will be a solid line. So this is the solid line we're referring to. That is the solid line. Now let's confirm. You have, if this is the line, the y-intercept is 1, and the slope 3 means 3 over 1. So 1, 2, 3, then 1 to the right. So this is actually the line here. But how do we know if this shaded portion is really the solution? We take again a test value 0, 0. So if we have the test value 0, 0, let's substitute that into our equation. Y is greater than 3x plus 1. So y is 0 and x is 0 plus 1. So 0 is greater than or equal to, this is 0 plus 1, it's 1. And this is a false statement. Again, if 0, 0 here is here on this side of the line, and we arrive at a false statement, that means we're going to shade this portion here. Okay. Process the information. So after graphing the two inequalities separately, we're going to find the intersection of the half planes. So notice that the solution to this linear inequality is the half plane. This is the half plane here. And the solution to the second inequality, y is less than x minus 3, is the half plane. Okay, it's the half plane below this boundary line. So the solution to this system, okay, the solution to this system is the intersection of the two regions and bounded by this dashed line and the solid line here. So any point inside this region is a solution to the system. Now let's find the solution to this system of inequalities. Y is less than negative 4x plus 1 and y is less than 3x. So we are given 4 choices here. And I will show you how to use the graphing calculator to facilitate graphing of these inequalities and find the region that represents the solution to the system. So if you have your devices, I want you to go to, to Google Desmos Graphing Calculator. And you can download this in your cell phone or your devices. So notice that we earlier graphed the two lines, y, okay? Y is less than 4x plus 1. So it's negative 4x. It's negative 4x plus 1, okay? See how fast it is to see the solution to this linear inequality. So we are going to graph each linear inequality separately. That's the first one. Notice that it's a dashed line because this is a strict inequality. Then the second line, okay, on this side here, you type a y, okay, y on the keypad here, y is less than 3x, okay. Follow? Now, notice again, this is a strict inequality. So you have the dashed line here. The blue region represents the half plane, which is the solution to the second linear inequality, y is less than negative 3x. Okay, so the solution to this is this lower, okay, the intersection of the red and the blue regions, which represents, this represents now the solution to the system. That's the intersection of the two half planes. Okay. So going back to the 4 choices, notice that when we graph the two using Desmos graphing calculator, the boundary, the region representing the solution was bounded by this dashed line here and this solid line. Any point on this region represents the solution, and this is now represented by this choice here, letter D. So this is one region intersection, another 1, 2, 3, 4. So of the 4 choices, number 4 represents the solution. So that ends our lesson for today, and your assignment is to practice graphing linear inequalities and systems of linear inequalities using Desmos Graphing Calculator. I hope to see you next week.